let me explain you what are the charge densities. When we say a charge, theoretically we mean a point charge. We assume that all the charge is located at a single point that we draw on our paper or on our board. That is the point charge. But practically, charge can be deposited over the line. It can be deposited on the surface or within the volume. So depending on which you take charge or within which you take charge, we can have three charge distributions: line charge, surface charge, and volume charge. When we deposit a charge, when we take a charge on the line, let us say a straight conductor having length L, in such case we call it as a line charge. We deposit the charge uniformly all along the length of the line, and in such case we define a line charge density or linear charge density. Its definition is very simple. It is the total charge upon the total length on which the charge is deposited. So rho L is given as charge upon length. For example, let us say I have 5 coulomb of charge and I have deposited it over the 5 meter of the conductor. Then my line charge density would be 5u by 5u, that is 1 coulomb per meter. It is very simple. Or let us say I have already given with the line charge density rho L equal to 5u coulomb per meter, and I am asked to find the charge contained by the 3 meter of the line. Once again, formula will be same. Rho L or line charge density equal to charge upon length. So total charge equal to rho L into length. So in our case, it will be 15 coulomb, as you can see on the screen. Now, my dear, this is very simple type of illustration that I have just explained to you. But actually, line charge density rho L may be a function of x, y, z, rho phi z, or r theta phi, whatever. It may be a function. And in that case, you cannot find the total charge merely by the multiplication, as we have just seen. In such case, you have to make the use of differentials. You have to make the use of integral calculus to find the total charge. And my dear, you are now familiar with the integral calculus. First of all, we find the infinitesimal value, the small value of the function, considering the small differential. So in this case also, we will find the small charge, the infinitesimal charge, considering very small or differential length dl. And after that, we will integrate that dq, we will integrate that infinitesimal function over the complete length of line by taking line integration. So this is how we find the total charge by line integration. Line integration rho L dl. Now you can notice one thing over here. We don't use the vector form of the dl. You know, we are dealing with the charge. Charge is a scalar quantity, and for the scalar quantity we don't need vector form of the dl. That's why we have taken only scalar form of the differential length. That is very simple. It is without unit vectors. It is dx plus dy plus dz. One more thing you can observe, we don't need to put the dot product in between, because we are dealing with the scalars. Line charge density or rho L is the scalar, dl we are assuming is also scalar, so there is no need of dot product. So this is how the total charge can be calculated when we are given with the line charge density. Consider the next question. You can read the question from your screen. In this question, we are given with the ring charge. Basically, ring charge is also the line charge, but in circular fashion. In the question, the line charge density is given as 5 rho coulomb per meter. It is also given that the line charge or the ring is present on the xy plane and radius is 4 meter. We are asked to calculate the total charge contained by this ring. Now, first of all, look carefully at the question. Rho L or line charge consists of the rho coordinate, which corresponds to actually cylindrical coordinate system. The ring is also in circular fashion. So what I'm trying to point out, This question can be solved with the cylindrical coordinate systems. And as you know the coordinate systems, in cylindrical coordinate systems, the coordinates are, or the variables are, rho, phi and z. So let us consider them rho, phi and z. Now, my dear, in this lecture I have repeated many times, for any given line or for any given path of integration, we always have only one coordinate changing or variable with respect to which we write the differential, and rest two are always constants. For example, consider the ring given in this question. It is given that the complete ring is present on the xy plane. Now remember the coordinate systems. For xy plane, any point on the xy plane, z coordinate is always 0. So for our complete ring also, for our complete line of integration also, z coordinate will be constant at z equal to 0. The next thing given in the question, the radius of the ring is 4. Now consider any point on the ring. Consider any small dl on the ring. You will notice that as radius is constant all over the circumference, for every point on the ring, radius or rho coordinate will be constant. So rho coordinate for our integration will be constant, and it will be constant at rho equal to 4. So my dear, for this integration, for this ring, we have two coordinates constant, rho equal to 4 and z equal to 0. So of course third must be changing. As you can also see from the diagram, the third coordinate phi is different for different points on the ring. Consider any small dl on the ring. You can see from the figure, phi is different for different dls. So what I am trying to point out here, we already know the dl or differential length for the cylindrical coordinates. It is d rho plus rho d phi plus dz. But out of these three differentials, we are only going to write corresponding to the change in phi. That means dl will be rho d phi. Rest two are constants. We cannot integrate with respect to them. In this question, only phi is changing. For different dls, we have different phi. Therefore, we can only integrate with respect to phi. So our dl will be rho d phi. And our integration, required integration, is converted as you can see on the screen. It will be phi u rho square d phi. Now let us put the constants into the function and let us put the limits. Now as you already know, you have to put rho equal to 4 and z equal to 0. We don't have z here, but you can put rho. Now for the limits, you have to put the limits for phi only. Actually, you can put the limits for phi only because phi is changing. Now the initial and final limits will be from 0 to 2 pi, because remember the cylindrical coordinates. If you have to cover the complete range, if you have to cover the complete circle, you have to take the maximum values, the complete values for the phi, and the maximum range for the phi is from 0 to 2 pi to cover the complete line. So putting that limits for phi and solving the integration, you can easily conclude to the answer, as you can see from the screen.